Hello everyone. Now we are going to discuss about one topic in Unit 3 TLR of subject. Unit 3 is nothing but high frequency transmission lines, impedance matching and high frequency transmission line. In this we are going to discuss about one Smith chart. Right? Impedance matching is very important in case of all the parameters, and transmission line is very essential. And impedance matching is done by using various circuits and transmission lines. A small section of transmission lines is used for impedance matching, and here the transmission line parameters are calculated by using Smith chart. Right? We can calculate the transmission line parameters by using Smith chart. And now we will see about Smith chart, introduction of Smith chart. Right? Smith chart, which is nothing but this is looks like on Smith chart. Right? This is called as Smith chart. What is the purpose of the Smith chart? The Smith chart is mainly used to find out the transmission line parameters. By using the Smith chart we can able to calculate the transmission line parameters, and also we can able to find out the stub length and stub locations. All the transmission parameters can be easily calculated by using this Smith chart. This is a graphical method. We can able to calculate by using analytical method, and also you can able to use by you can calculate by using a Smith chart. It's nothing but a graphical method. So let's start our problem. And here determine the following: standing wave ratio, load admittance, and the distance between the load and first voltage minimum along the transmission line. And the given parameters are the characteristic impedance is 300 ohms, and load impedance ZR, which is something like ZL is equal to 175 plus J207 ohms, and the frequency of transmission is 200 megahertz. And from this frequency we have to calculate the wavelength value. And this wavelength is lambda is equal to C by F. C is nothing but 3 10 to the power of 8, and lambda F is the operating frequency, which is 200 megahertz. 200 10 to the power of 6. If we are going to calculate the value, we will around get 1.5 meters. Right? And we are going to mark this load impedance value in a Smith chart. If we are going to consider about the Smith chart, the size is restricted. The Smith chart size is restricted, so we are going to do the normalization of given impedance values. Right? And the complete circle of a Smith chart is called as a 0.5 lambda. Our complete rotation of Smith chart will be considered as 0.5 lambda, and here this is 0 and this is 0.25, and again we are going to consider 0.25 lambda, and this 0.5 lambda 0.25, and one complete circle represents 0.5 lambda. And in Smith chart we have two values, right? One is two circles. One is constant R circle, another one is constant X circle. Constant R circle is the resistance circle, and constant X circle is the reactance circle. Right? Constant R circle is the resistance circle, and constant X is the reactance circle. And here you can notice that this horizontal axis called as resistance circle. Here we have a 0 value, 0.1, 0.2, 0.3, and like we have a center as 1.0, and 2, 3, 5 we have a maximum values. And imaginary value, imaginary circles, right? It's a X circle. Here we have 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8 to 0.9, 1. Like we have a 2, 3, 5. We have more number of values. And this complete circle is considered as constant R circle, and the butterfly circles are considered as imaginary circles or constant X circle. And we have two reactance values. One is inductance reactor, another one is capacitance. So if the complex load is the positive, means it is considered as the inductive load, and if the complex value is considered negative, means it is considered as the capacitive load. Right? And we will go for the problem. First you have to do the normalization here. ZL by Z0 is equal to ZL is 175 plus J207 divided by 300. Just we are going to divide by the value by 300, so we can write in terms of 0.5883 plus 0.69. You have to mark these 2 points on a transmission parameters in terms of Smith chart. this 0.583 is marked here. So here we have a 0.5 and this is 0.6. So you have to move the line upward direction. So this point, this is the constant R circle. This is 0.5833. And next one is 0.69, and here we have a 0.6, here we have 0.7, and here you have to drop the line like this, right? If you are going to drop the line like this, here we have a point value. So the 2 points are intersects here, so we are going to mark the line here. This is the point normalized load impedance. So right, normalized load impedances ZL is equal to 0.58 plus J 0.69. Then we have to take the center O as a center and P as a radius and draw one circle. By using compass, you have to draw one circle, right? And then the circle cuts the horizontal axis in the right hand side, right? This point is considered as ZWR. You can write the value by seeing the chart, which is 2.8. So which is given as 2.8. Next, the second parameter is the asked load admittance value, right? So here we have load impedance. Just you have to draw an opposite line from this center. So starting point P and through center O, you have to extend the line. So the opposite, you have to draw an opposite line. So that line cuts the circle in this point. So here you have to mark the real part value. So here you can mark the real part value like this. You can point out this value here, and imaginary part you have to mark like this here. So we can write a 0.78 here. This value approximately it is 0.78, and due to the load is available in a downside, so we can write in terms of minus 0.86J, and this is the normalized value. So you have to find out the actual value. So it is given as y by g naught is equal to y into z naught is equal to 0.72 minus j 0.86. So this is the normalized value. We have to do the unnormalization, right? So this y by 1 by z naught can be written as in terms of z naught. 1 by g naught is equal to z naught. Again we need the value of y only, so z naught comes into denominator. 1 by 300 into this value, so we can write the value as 0.0224 minus j 0.00286 more. And the third question is that the first voltage minimum from the load, right? Here this is the voltage minimum and this one is the voltage maximum. So you have to find out the value of the load, the distance between first voltage minimum and the load. So from this point you have to calculate the distance to this load. So just we are going to extend the line from O P to outer circle. Just we are going to extend the line, that's all. And then I have to extend the line like this. And already we know about the one complete circle is 0.5 lambda. From this 0.5 lambda you have to subtract this 0.114 means we will get the remaining value which is given here. So 0.5 lambda minus 0.114 is equal to 0.36 lambda, and we know the value of lambda is equal to 1.5 meter, and if you are going to substitute the value means you can obtain as 0.58 meter. That's it. This is the Smith chart basic problem. Thank you.